Presented by Caltech.
Hi everyone, and thank you all so much for coming. I hope you are as excited as I am for this talk. I would like to introduce you to Mimi Ong, who is here to talk about the Mars Helicopter Scout project. Mimi Ong is currently the Autonomous Systems Deputy Division Manager at JPL. She completed her education at the University of Illinois and has great expertise in autonomous systems guidance and control. She has been with JPL and Caltech for a long time in numerous roles. And in that time, she has been the manager of the guidance and control section. She has served as the project element manager for formation flying technology for the terrestrial planet finder mission, as well as the manager for the autonomous formation flying sensor for the Starlight mission. So please welcome Mimi Ong.
Thank you. Okay, well, thank you very much, Michelle and Maria. Everybody, thank you for coming. I'm very excited to talk to you. So I'm going to present today the Mars Helicopter Scout, which is a proposal to fly a helicopter at Mars. And we're proposing to launch it with the Mars 2020 mission. And it is a proposal at this time under discussion at NASA headquarters. We have not been selected or decided upon yet, but there is ongoing discussion. So I'd like to also acknowledge co-authors for this page, the chief engineer for the Mars Helicopter Scout, Bob Balaram, and then the original PI, science PI for this original proposal, which is Matt Gollenbeck. Three of us usually tag team on presenting this. So anyway, I'm presenting for all of us. All right, so I'll present it in this order. I'll introduce it to you and go into a little bit about why the Mars Helicopter Scout, and then after that go into what it is and the question of will it work. We're convinced it will work. I just want to share with you the overview of will it work, and then I'd like to really engage you in the end about what about the future? I mean, why a helicopter at Mars? And in fact, your inputs and your thoughts would be appreciated at the end. Okay, so the Mars Helicopter Scout, by the way, we need a better name, we've been told. They said it's not exciting or whatever. So anyway, if you have names, it's going to scout ahead of a planetary surface rover to provide high-resolution aerial images. Okay, so the thought is for a high-resolution camera to complementary to a rover, be able to fly far ahead of the rover to get high-definition images more than we do today, so that we can use those high-definition image information to first decide which site we want to go to get the best science, what kind of science we expect when we get there, and that's the science side, and then operational side, because once we decide where to go, getting really high definition images between where the rover is and where the site we want to go, for kilometers, we can actually turn them into three-dimensional terrain maps and then plan better operations. So it's our intentions are twofold. So needless to say, I mean, this is a game-changing proposal that we're making. We're very excited. State of the art is to drive rovers, right? But this would be just like on Earth, right? We drive cars, but we have planes for the faster traverse to go further, to look at it. Adding this aerial component to exploration of a surface of Mars is something that we're very excited about. Okay, so the proposal is to demonstrate this new mobility technology for Mars exploration. And demonstrate a first-of-a-kind science and operations utility. And again, I want you to keep in mind this is a tech demonstration, the first proposal, but it leads to many future expansions that you probably make a list longer than I can. So, and of course, validate this concept and pave the way for the future. This is a functional overview of the helicopter, and we'll get a little more into details later. There's a full-size mock-up here. So this is a full-size, and the plan is for the nominal flight, for this version to fly 2 to 3 minutes in duration, okay, per day. And the nominal altitude is 600 meters, going down, half a kilometer to a kilometer, basically. Fly 40 meters above the ground and fly once per sol, and then spend the rest of the day charging up. It's a self-standing system that I'll talk about. And instrument on here in this that we propose for this proposal is a high-resolution color images of the terrain and a very low mass, very light but high-resolution camera, okay, to fly that. And if you think about that, and I'm saying the word nominal because it's a very powerful tool. If you think of a helicopter platform carrying a camera, as opposed to you just having a camera fixed, on the ground or on a rover that's moving slowly, I mean, you can actually vary the height that you fly in, and then the baseline that you form, to get the different pictures from different angles and the different lengths, right? So it's a very powerful, flexible trajectory that you can actually command to get your series of images. Okay. So the helicopter is 1.1 meter in diameter, okay? And then the chassis that you see here is 14 centimeters per side, and the mass, the total mass, including everything, the rotors and everything it has to lift, and the camera, everything, is approximately 1 kilogram. The power that it's going to consume, which, by the way, it has to generate on its own through the solar panels and charge the batteries inside, is 220 watts. The data will be, a lot of it will be stored on board, and some of the data from the images taken will be sent back to an interface box on the rover during the flight a little bit, but primarily while it's on the ground. So the idea is to land this rover. This is a notional accommodation that would be possible in the 2020. To have the rover, and it gets actually slid down and flipped and dropped very nicely, but this is a nice way to be tucked in, carried, okay? And then this part will be dropped on the ground, okay? And then the rover will drive away. And from that point on, this helicopter is to be a standalone instrument. It never goes back to the rover again, which means it has to survive on its own thermally, power-wise, and it has to be able to, the only thing will be the RF link between the rover and the helicopter to give it trajectories that we wanted to follow and that, to get the images back. Okay, so this part will be dropped, the rovers will drive away, and we will leave on the rover an antenna and an interface box through which we'll communicate. And so it's a standalone, and we say that because it's a very significant point to make in that to Mars 2020 rover, we're not using the telecom link or anything. The only thing is we talk to our own box, and then they talk to us like they talk to any other instrument that's attached to them. Okay? So with that high level, one other high level concept that I want to introduce to you is the helicopters that you see that are very common is shown traditional on the left, and what's being proposed is a coaxial helicopter. So the difference is the traditional helicopter, right, has a primary rotor on top, and the torque that it imparts is counteracted by this tail rotor, right, to make sure to kind of push it back up. And so that's the traditional helicopter. What we're proposing is the torque that's imparted, is canceled by another rotor that's turning in the opposite direction, okay, completely phased. And the reason for doing that is in the very beginning, the team traded traditional helicopter, quad rotors, and the coaxial helicopter. And this came out the best for Mars cases where we really need a very low mass option. I'll talk about that a little bit. Very low power, very easy to accommodate in a rover before we get deployed, and then the high performance. One thing I also want, which I didn't really pay attention to until I started working on this, I guess on Earth, right, we have landing pads for helicopters, to land. And so we don't have that at Mars. And so, the whole kind of having clearance and how easily we can land, coaxial configuration really allows for more options. Okay. So a little bit of time on why a helicopter scout. So this is an orbital image taken from MRO, through the HiRISE camera of Endeavour crater, the edge of it. Okay, and this is a resolution, and you can see that there are some outcrops. Okay, some areas of interest, but this is a resolution as good as it gets. So traditionally, you would say, okay, from orbit, say this area looks rich in outcrops, but the actual content of the outcrops for the scientists, I think there are probably more scientists that know a lot more than me. I'm sorry, I'm an engineer. The actual detail, it doesn't have the resolution. So we end up, taking the rover there, and for example, in this case, Opportunity spent about 100 sols walking about to find the area of interest. Okay, the kind of resolution, so this is about 25 centimeters per pixel when you're on the orbit, with this kind of camera we're talking about. But this is the kind of resolution that they got once the rover got there, and that's the level they need to find out, the prehistoric, when, like the whole how was it habitable, and all the science questions are answered. You need this resolution, which is more. So what we offer is more like 3 centimeter per pixel, like an order of magnitude better in resolution, so that we can actually fly the helicopter there and get this kind of information before spending 30, 100 sol getting the rover over there. It's a major advantage. Another example, this is at Victoria Crater. Opportunity spent 340 days scouting the North Rim, and then finally finding an ingress point that everybody was happy with for mapping stratigraphy. And when we talk about flying, 600 meters per day, we can cover with calibration and all of that in 10 sol. So it's a very, very big difference. Another area that scientists, are very interested in is the geologic relations, key geologic relations between different types of information, different rocks and formation, and also the context, the geologic context, or where was this data taken from, so that you can correlate it to other information. And this is where you can imagine, right, a helicopter can go places that rovers can't go to get these images. It's very powerful, okay? And then, so that's on the science perspective. Once you get all this data ahead of time and get to the science target, to plan the path. Okay, again, helicopter can provide these high-resolution images that can be sent back to Earth, and then the rover drivers can use those to do 3-dimensional reconstruction of the terrain and tell us, how to drive. This is an example of Curiosity when it came to Dingo Gap, and this happened on Sol 527, and there was some sandy areas that they were worried about the rovers. There were some jagged rocks that they were worried for the wheels. The whole decision of, okay, should we go ahead and risk and get to this side, but what's on the other side? What if we get there and it's the same over there? A helicopter, for example, images from there, high resolution would have been highly, useful for that, okay? Lastly, a helicopter, this whole operability, the traverse, how fast you can drive per sol. Okay, that is also affected. And this is an illustration. This is a picture of the Arroyo next to JPL. And I'm showing that because a quad rotor flight was done, and a couple of the people who did it are here in the front. And so, but this is a picture, a notional circle of typical MSL, using the nav camera on the rover. From seeing that, you can go blind driving about 100 meters. And then per day, okay, per sol, and then another couple tens of meters beyond that, not blind driving, but using the auto nav on board, okay. But if we were to be able to get data from, say, 400 meters down or 600 meters down, then the length that you can blind drive, extends by that much. So what happens is then we took a Scout Cam prototype of the equivalent camera that we are willing to fly, the low mass camera, and we wanted to show that this is feasible. So the quad rotor took the camera and flew at the 40 meters, and then those images were processed and put into the RSVP tool. That's the software tool that Curiosity and Opportunity and those rover drivers use to actually generate the 3-dimensional terrain maps. And then they actually use their tools to do a rover safe plan through that, and then demonstrated blind driving. Okay, and again going up to 400 meters. So there is the Scout Cam on the quad rotor. It's in flight about 40 meters up. And then these were the images, the left and right stereo pair, just from the path. And these are the data products that came out of it. And after putting the products together, this was kind of the 3-dimensional stereo terrain mesh, and that they put into this tool, the RSVP tool, and simulated a blind drive. So compared to the 120 to 140 meter per sol kind of blind driving plus some of the auto nav, we are demonstrating that you can enable 2 to 3 times better. You can go further per sol, with this kind of help with these high resolution images. Okay. Unfortunately, I wasn't able to make the movie play for this, but there is a nice full simulation in the RSVP tool. But this was part of it. So, okay. So. Hopefully you're as excited about it as we are about why. So let's talk a little bit about what is it. Okay, so it is a coaxial helicopter, and it is designed to fly on Mars. And the they are supposed to be made, the shapes and the size are all optimized to be able to fly in a very thin atmosphere. So the Mars is at like 0.012 kilograms per meter cubed, like 1/100th of the density of the Earth here. So when you kind of flap, your arm or a wing or something, it just doesn't. The lift is not as much as here, and so the biggest challenge is to lift. So that's why you'll see that was one of the first demos that we addressed. Okay, so the question, where does the 1 kilogram come from, right? So when you fix the rotor diameter, and that comes from the rover accommodation. So I want you to keep that in mind. Okay, the bigger you make the rotor to a certain extent, the more you can lift. But we are limited on a tech demo basis how big a helicopter can be, right? Because of the space that the rover has to accommodate us. So the length that we can work out is up to about 1.1 meters. Okay, given that and the Mars parameters, our calculation, the aerodynamic calculations show that we can lift about 1 kilogram, and then plus some margin we can allow. That means now the entire vehicle can weigh more than 1 kilogram, so 2.2 pounds. I mean, it's not very heavy. Okay, so it's a very, very interesting challenge, and so we've been looking at that. So another thing is, remember I said it gets dropped off by the rover and we never go home again, right? We're on our own, adults at that time. So it really has to have its own solar panel, and so the solar panel is kind of right now placed where there is least aerodynamic action, at least that that we can put. It converts solar energy into power, and we have batteries inside. We have inside that holds to that 220 watts. And because of that, we will be flying about 2 to 3 minutes per day, and then spend the rest of the daytime charging ourselves. Okay, so it's a very fine line we're walking. It has to survive at night, so there is aerogel insulation to keep it warm. Again, it can't get too cold, it can't get too hot. Okay, it has to be challenged. And then in terms of flying it, okay, what the mode of operation is, then we tell from Earth after we get these images and say, oh, looks like this is the best way to go from here to over there. Here are the waypoints. Follow these trajectories, right? And so the helicopter will take off, start flying towards those waypoints, but it needs onboard measurements to make sure it's staying on track, right? It's totally autonomous. We cannot joystick it, right, from Earth. And so what we're using is the camera, which again we use for science and operational images purposes, but we'll also use it for navigation, and we'll use the IMU and altimeter to measure the height. So we have a gyro and an accelerometer and the altimeter, and then use those to keep the helicopter on track. And also at the end, remember the reason I said there is no landing pads on Mars, you do have to land somewhere flat and away from rocks. So we do have to be looking on the ground and using the camera images with the motion, giving you perspectives from different angles, reconstruct and find out where the hazards are. And at the last, few, tens of seconds or under a minute, do decide that the place we decided to land is safe, or if it isn't, do a quick calculation of a divert, to land to a safe place. So it has to have smarts, but again, we do a lot of this on spacecraft. So entry, descent, and landing, rendezvous and docking proximity operations. These are not things that are strange to us, but we're doing it with a helicopter. So okay, and then we talked about the camera, and then the landing system. Again, it has to be resilient. We are designing it because of now are you starting to feel like mass constraint? I'm hoping you're feeling the pressure that we're feeling, right? I mean, we can only put the helicopter where the rover can give us. So we can have these self-riding systems, not this time anyway, for this version. So the trick is to design landing systems that are resilient. So maybe it lands faster and harder than we think, but okay, add some spring. Okay, it might be tilted more than we think. Okay, we need a forgiving kind of landing leg. So those are the landing legs there. And then the radio. The radio provides a link back to our interface box on the rover so that we can send our image, and also so that we can command. And so that's what makes up the system. So it's a really fun system. Okay, we have the atmosphere to think about. We have We'll talk a little bit about winds and some dust conditions that we have to talk about. We've been doing a lot of analysis to show that we've come up with kind of a balance between a resilient, robust system and onboard smart control. So that's what we're proposing. And on top of it, because of the very low mass, remember this 1 kilogram really dominates. So like our chief engineer, Bob Belram, in terms of counting changes in dollars, he's counting in grams. Like, how many grams more? How come you're violating by 2 grams? It's literally. So it really is about low mass. And so we're having to use a lot of the low-cost commercial parts. They really are advanced. You can think about the cameras. You even have on your phone or the GoPros that are out there. You can talk about the computer chips that are on your iPhone. We're taking advantage of those technologies to get there in a very light solution because our traditional spacecraft solutions just don't lend to this innovative platform. So we have parts selected, and we've been evaluating, and everything is hanging together in terms of mass and the power and the performance. Again, the idea of the helicopter operation, there's a keep-out zone around the rover. We promised the rover we'll stay away from it so that we never, this is a tech demo, so we'll be operating from afar. Now, they'll still be able to see us and take pictures of us and send it back to Earth so that we can see ourselves flying. And so there'll be a daily battery recharge, and then the 2 to 3 minutes of flight per sol. We'll take off, and then fly about 2 minutes, and then come down. And this can go, we may start. This is a concept, is to say, okay, we first start with somewhere where we know. The rover leaves us somewhere flat and nice and safe, right? So maybe fly 2 minutes and come back close to where we started. But as we get more experience, remember we're getting images all the time, right? We can get braver, and you can see this curve going further and further out, and we don't have to keep coming back where we're coming. Again, think about how powerful this tool is. You can absolutely control design the trajectory, the path that you want it to flow so that you get the kind of information you want, right? And again, I talked a little about onboard autonomy that's needed, to keep you on the trajectory, the path that you planned, and then look at the images, and they're paired, and then you do a 3D reconstruction to determine safe side and to land. Thermal design, this is not an accurate design, just giving you an idea that inside the chassis you see, right, we have the aerogel, but inside all the electronics are actually in a very small cube. I think it's about a 7 centimeter per side cube. So all the chips, all the batteries, so the gyros, accels, all of that have to fit in there. Okay. And this, I'm not going to keep this curve here. I just wanted us to recap kind of the technical design with this picture. Okay. When you have that 1 kilogram mass constraint and the atmospheric density and the size, and remember this is an electric vehicle, it's kind of generating its own power, and so if you need to lift more mass, you can always do it by turning the rotor faster, as long as you don't exceed the speed of sound. Okay, there is a limit too. Okay, so the rotor can be going faster than the speed of sound. So between those constraints, you can play the game. So let's say you need to lift more, right? Then you're going to need more power. But guess what? When you need more power, then you need bigger solar cells, unless you can get them more efficient, and then you can get the bigger battery. So it's kind of this fine game. And but you can save power by, if you can make the rotor turning more efficient, we can play with the efficiency of the rotor. You can play with the size of the rotor. Or you can play with the time of flight. Let's say we run into an issue where, we're too big. Oh my, we have to. So there are all these kind of different ways that you can optimize the system, and that's a game that we've been playing and understanding the sensitivities. And so that's what the curve was just saying, that nothing comes for free. Okay, so if you go up more in power, your mass will grow, and it's just showing. Right now we have margin, but again, we have to be very flexible, and we're going to have to be very agile. It's the first time nobody has flown an aerial vehicle on another planet, so we're ready to learn. Okay, so the question of will it work? So the biggest, as I mentioned just now, I think the first question, I think somebody just now said, I think Udon said that, hey, I don't even know, is this possible, right? So it really is, the first thing is aerodynamically, is it possible? And so this work started way back as late as, I think Bob Belram started in 1999. There's some work that started there, and it's been all pulled back up. And so the idea of feasibility has been around, since the late 90s, kind of. And so since the 2013, when the JPL has become serious about pursuing this idea, now the electronics have become better, smaller, more capable. This is the right time to push for this. We've dug it up, and so there have been like the blade characteristic, this airfoil, that's going. Can it lift that analysis? So there have been some CFD analysis done, and then there was a static test done with, you command it, put it in a chamber with Mars-like atmospheric density and see how it responds. That test was done statically, and then we tested it with kind of a strain two sides and saying, can it lift? When you turn the rotor this fast in this atmosphere, does it go up? And it worked. So then the next step we did was to say, again, we're not adding control yet. Just instead of having on rail system, do a free flight system, just a very fast. It's not tuned for Mars or anything, but at least to say for this size, at a given revolutions per minute, it should lift freely. We did that experiment last year, and they were all successful. And in parallel, we've been looking at the whole control system, right? Given the thinner atmosphere and the low Reynolds number, and how does the blade interact, and how controllable is the blade, interaction between the blade and the atmosphere, and how amenable is it to being controlled. So there's kind of the control analysis that's been going in parallel, analysis and simulation, while the blade's been characterized. And the next big activity we're proposing, and this would be a part of the flight development, is to first do the 1 meter system, fly it in a chamber, closed loop control. Okay, so it would come to that. So with that, I just want to show you a movie of this free flight test, right, that we did. It's a scaled, remember this is about 1 meter. This is a 1/3 scaled vehicle that we built very quickly, right, within a few months. And just to make sure that, and then pump down this 25-foot chamber at JPL down to the Mars atmospheric density. And then asked it to, lift, basically turn, it's so many like 7,000 RPM. And at certain RPM, it should lift. And we're glad to report that, yes, it lifted at the RPM we predicted. So, okay. But I want to just also give you a heads up. This is not a controlled demo. So you're going to see it just has to lift, and then the operator shut it down, and then lift again and shut it down. But our next goal would be to have it fully controlled, but also with the full size, the 1 meter. So this is the 1/3 meter demo. And how do I find? Oh, I see. I just click it like this. And there it spins, and then it lifts. It lifts about 2 or 3 times the rotor diameter, right? So this was very, very good news for us. This is totally in the Mars, 0.015 kilograms per meter cube environment. And so we were very happy that it lifted when it was supposed to. And then the very last one, the operator didn't kill it in time, and it did crash. So but I didn't want to put it up here in case it got ingrained that we designed it that way, but it's an experiment. So anyway, we were very happy with that result, but we're eager to do the full size and closed loop. And the closing the loop now would mean lifting it with the more Martian, atmospheric optimized blade, being able to command it real time, the blade directions and the speed, and feeding back from the real time measurement of, where the coaxial vehicle, the helicopter is, and being able to control it real time. It has a lot of challenges around it, but it'll give us, and it would bring all our simulations onto the test bed for real. So the challenges is robust landing in the presence of wind. These are just top-level challenges, but we have to think about Mars. So we plan to schedule flights for favorable winds, like less than 5 meters per second, and we'll use the predictions from the rover. There's a metrology station data that they have, so we can use that data. Also, because of you can see the legs, the 4 legs, and kind of tugged in. It is flexible. It's designed to withstand, when it's sitting on the ground, up to 45 meters per second stable winds, which the wind experts said is a reasonable assumption for a good worst case. So those are the things we have to talk about. Accurate scaling from Earth model to Mars. We can never have this 1/3 of the gravity at Mars, 1/100th of the atmospheric density, and the composition. The whole is different. The slightly different Mach the sound of speed on Mars and all of that, all in the same environment in one experiment, right? So everything has to be scaled. So it isn't like we can build like a third scale and say scale everything down and put it into a Mars chamber, but it kind of scales kind of non-linearly across all the parameters. So the scaling is the challenge. And that's why we will have to do test as you fly exception, just like entry, descent, and landing, right? When we land at Mars, we have many simulations. We have many hardware tests. We have field tests. We have testbed tests, right? But they all have to come together and have us, check off different angles that we want to check. But we can never do, real EDL simulation until we really get to Mars. That's our ultimate field test when we get to Mars. It's the same thing, the helicopter, because of the different, the way different factors impact. But again, we've done it before, and we're employing all the EDL techniques into this. And so in our proposal, this is a technology demonstration. We say the vehicle is capable of 1 flight per soul, each one up to 600 meters. Again, altitudes from this 10 to 100 meter, altitude. Minimum success is 5 flights, okay? Having said that, multiple additional flights are possible because there are no consumables, right? I mean, it's a solar panel charging the battery and the battery recharging when it's being used. There's software that we can tell different we can command from the rover different paths to follow, okay? So given that it isn't some fuel it's using up or any kind of supplies that could run out except aging or other things like that. The most likely, if you ask us, how do you think this mission will end, is it'll crash land or it'll tip over. And this is where I really crave for these self-standing systems that we just don't have the mass or the volume yet. I think you've seen these toy quadcopters that they land and then they have a self-riding and the kids can start controlling again. We don't have the self-riding. So this is how we think the mission. But if we're careful, I mean, it could go on for a long time. Okay, so this is what we are going for. So, having said that, I guess this is the part that I really wanted your attention, and even if your ideas and thoughts and suggestions. We're certainly not doing this for a one-time fun or a game. It's really, to us, we believe in this because this is the first step in breaking that aerial component, right? And it just, things will be so much faster. Yes, rovers are great, they can go far, but we can go that much faster, we can go that much more, and they're complementary, right? So it really has a lot of feet forward. And there was a list, longer list, but here are a few examples, right? Like Mars free roaming helicopters, okay, that talk directly to the orbiters instead of just talking to a rover, okay? That could be it. Or the second one is a sterile autonomous helicopter. So there are like biologically very interesting and very sensitive areas that we wouldn't send our rover close to because we can't clean our rover, something so big, as clean as we'd like to, and we wouldn't want to introduce our organics into Mars or anything. We don't go close to somewhere like, with a rover. But a helicopter, if you make it small, so that if we stay small, something like this could be sterile. It could be sterilized and actually packaged and then not open until it gets to Mars, in which case there is a slight hope that you can actually get a vehicle close to very interesting areas of science. These are all thinking far beyond what we do today. Okay, and then how about the larger, rotorcraft missions? How big can it get? The first analysis show easily to 500 kilogram, class of spacecraft. At some point, it becomes a spacecraft of its own, and all the rotor efficiencies and all that. There will be an end, but it could up to 50 kilometers. It's looking very good and getting bigger. So you can see as you have much bigger helicopters, like on Earth, you can see more sophisticated instruments. That could be put on. Titan, Venus have atmosphere. We could have applications there. Human exploration. Surveillance helicopter for humans, living on the surface or exploring on the surface, right? Again, I mean, instead of just waiting to see what you can see on top of a mast, you would like to actually joystick. In that case, he could joystick, actually. He would be there. Joystick a, helicopter and go see where you should be going or what's going on. Another idea, I guess, is let's say there was a Phobos outpost instead of people settling on Mars. Can you joystick a bunch of helicopters? Now you're talking within range, So these are some of the out-of-the-box thinking. And then definitely even in earth science, we have synergy with autonomous drones. And so evolution of Mars exploration, for example, we've come a long ways, right? We started with the orbiters, which are still very important to us. Very wide area. You can see, right, almost globally or a big fraction of the planet, but low resolution imaging. You saw the capability. You can only see so much at that high, hundreds of kilometers above, okay? So then we've come to landers. And then we have had like Viking kind of lander where single location, no mobility, but you can do locally very high resolution, right? Then we've come into rovers where limited mobility, I mean limited meaning 10 kilometers, maybe 20 kilometers, but unless we can accelerate in that dimension too, but locally very high resolution, right? So the 2020 proposal that we have right now is here, which is now rover paired with the Scout, right? So efficient mobility, go further and still work with the rover in a complementary fashion. And again, wide area because you're going to be high, you have the altitude, you can look much further. And high resolution imaging. And then here are the future that I really want you to think about and give us suggestion, or you should actually expand your imagination now. If you don't have to just stay with orbital images for your experiments that you're interested in and not just stay with the rover, but now if you can put an aerial vehicle, how would you use it? Okay? You can think of fleets, multiple helicopters going to different regions and gathering the information very quickly. Again, the biological sensitive zone exploration, or very big, long range, like 50 kilograms, 100 kilogram class kind of aerial vehicle. So, with that, I hope I have successfully shared with you our vision that this is a modest start to breaking the aerial dimension of exploring another planet. This should be just the beginning. But if we're able to succeed it, this will lead, just like the little Sojourner, remember that nobody wanted to put on we don't want that, silly thing. We got other missions, other important mission things to do. And the Sojourner actually, we learned that, rovers really are very effective. It can get us away from the fixed stand. We can go further. We really have a lot of hope in this, both complementary to the rover and standalone. So thank you.